welcome to the first of 4 lectures on the Brownian motion. So in the first lecture, I always like to play this video. This is from YouTube. I think it's, if you search for maybe Brownian motion simulation, you'll see this. This was simulated on a computer, and so by now what's called the Brownian motion is exactly what's being traced out there by this blue dot. That path is what's referred to as a Brownian motion. It's continuous in this jagged kind of path. And our goal will be to describe this stochastic process that this represents. So describe it mathematically. That's going to be the task in this lecture. And so here maybe I can mention a few of the kind of the historical details and the background. Sort of the usual story told about this is there's this biologist. His name is Robert Brown, and I think the year is either 1821 or 1827, something like this. At least that's the reference to one of the papers that he wrote. And in that paper, what he's doing is describing all these experiments that not just him, but a lot of chemists and biologists were working on at that time. And what they were doing is taking pieces of matter, specifically inorganic matter. That's actually important. So think of like a piece of chalk or like a particle of charcoal, maybe anything that you think of maybe as a piece of sand or something inorganic, and you suspend it in some type of liquid. Maybe it's water, maybe it's wine, maybe it's alcohol, whatever it is. And then you look at this in a microscope. So I guess that technology was there in 1820. And what he found is that you take something that's not living, inorganic, you suspend it in water, which I guess has all sorts of connotations about giving life, and you see that the particle starts becoming lifelike. So it starts having this jagged, sort of erratic motion, as if it's, I think the word they used to describe it as dancing. So I guess you can kind of imagine all the speculation. They didn't really know how to explain this, but they posited, I guess, all sorts of theories, and contemplated, I guess, the difference between the living and the non-living, and what does it all mean, and why is it when you take an inorganic thing and put it into liquid, it all of a sudden sort of comes to life. And this was, I guess I don't know exactly the year when the term Brownian motion was coined, but it was sometime in the 19th century. But then as you turn to the 20th century, 1905, there's this famous paper by Albert Einstein that explains the Brownian motion. He doesn't actually, he's credited by now with explaining it, but that's not really, he never actually took credit. I think in the beginning of the paper he sort of mentions the Brownian motion a little bit and says maybe what I found is related to the Brownian motion, but I'm not sure, something along those lines. But the explanation that he gave is the one that we're going to discuss, or we're going to try to capture it or write it down mathematically in terms of mathematics. And the idea is that when you take a particle and suspend it into some medium, liquid, that medium itself is made up of further particles. And so these red dots that just came up on the screen, you can think about those as the molecules that make up that medium. So H2O molecules, or alcohol has a different, I guess, molecular structure. But the point is that whatever medium or liquid, or maybe even a gas, that you suspend something into, that thing is now surrounded by many particles. So as is the nature of matter, right there, you don't see it under a microscope. When you look at this in a microscope, you don't see H2O molecules, at least not in 1820, probably not even now. So you can't see them, but they're there. That's what the physicists tell us, and they're moving around. They have some energy, so they're kind of hopping about. And what happens to this larger particle is that it's getting bombarded. That's the term that you see in kind of describing this. So this blue particle can get hit from the left. It can get hit from the right. It can hit from above, below, front, and back. Right. So in this three-dimensional space that it's moving in, it gets hit by these red particles that compose the matter that it's in. And as it gets hit, it's starting, it gets displaced, right? Every single time it gets hit, it moves a little bit, and so on and so forth, and so you get, kind of, you can picture how this gives rise to this jagged motion. And so the model that we're going to try to posit for this is what's called a random walk. That's basically not in those terms, but what was basically proposed as an explanation by Einstein. So, and he's given credit as sort of being the first person to explain it. Yeah, and so just to give you a little bit of a kind of breakdown of the lecture, we're going to, kind of cover the introduction to Brownian motion. You should also be reading Ross. So the first 2 pages, I'm mostly going to be trying to fill in the details of the, this is page 1 and this is page 2, and I'm mostly following this, but slightly, with more detail than what's done here. I think, does he mention Brown? I don't think he mentioned Einstein there below. So, oh no, maybe he does mention Robert Brown. Yeah, so it's there. So, where was I? Lost my track of thought. So this is the breakdown, is to introduce the Brownian motion. We're going to cover Einstein's derivation of it, which is similar to Ross, but I'll go into more detail. We'll come up with the transition probability for the Brownian motion. It's going to be a Markov process. It's going to be living in continuous space and continuous time. And we'll go over, its properties. That's going to be, if you want to do mathematics with the Brownian motion, you need to get a handle on the basic properties. That's what I'll cover, and then I'll relate it a little bit to the Poisson process at the end. When speaking of the Brownian motion, the letter that's usually used is W, or the letter B. So B for Brownian motion. W is actually for what's called the Wiener process. It's, if you read the text here. Yeah, so this was, I think it's Norbert Wiener, I don't remember his first name. So he, had this series of papers, like it says, originated in 1918, and they kind of describe very specifically the path of the Brownian motion. And so W is a letter that's named after him, and B is, I guess, is something after Brown, and Ross in the end, I think, chooses the letter X. So it doesn't matter which letter you choose. The path of the Brownian motion looks kind of like this. You have the state space on the y-axis. It's going to be all the real numbers. It's a first example of a non-discrete state space. And T is going to be our time index, and this is what the path looks like. So it's this jagged path. So this is in 1 dimension, and the video was in 3 dimensions, but the basic idea is the same. So I guess I'll start with relating this to Markov chains.